Welcome back to our continued discussion on this atmospheric atmospheric boundary layer and finding out the lapse rate. So this is where actually we stopped in the last discussion uh, where we wrote from assuming the ideal gas flow system of unit mass, which is going through an quadristatic change of state. So using first law of thermodynamics, we wrote this where actually T is temperature, Q is heat transferred, here U is internal energy, H is enthalpy, and this V is specific volume, and Cp is constant pressure specific heat. Okay, these are the parameters that we have. Now, if you consider the process is adiabatic, that means there is no, so which means dq would be 0. Okay. If we do that, then from here we get Cp dt minus 1 by rho dp. So that gives us 1 by rho dp. So what we can do that, we can so replace this expression in this particular one. So we had also, let's say we had dp equals to minus rho d zz. So these two combining, we can get dt by dz, obviously adiabatic, g by cp. So that's what we get. So if I dt by dz, adiabatic is g by cp. So let's say the g and cp, this variation with elevation is assumed to be negligible. Then the change in temperature under adiabatic condition is constant. So if you put a standard value of G, which is 9.81 meter per second square, and Cp 1.005 kilojoule per kg Kelvin, then what we get dt by adiabatic is minus, we miss the minus sign here, so this has to be minus, so this becomes 98 by m degree C. So this typically gives the temperature decreases with increases. So this tells me, so temperature decreases when elevation. So with the increase in height for a system with no heat transfer, this is minus dt by dz. It's a 1 degree C per 100 meter. Okay. So that is what you get. And this is what is known as lapse rate. So this one has to also, be very specific. It is a dry lapse rate because the dry adiabatic lapse rate is quite important in meteorological studies since a comparison of its value to the actual lapse rate in lower atmosphere is a measure of stability of the atmosphere. Since actual atmospheric condition will have moisture and other things, so comparing that would give you the stability of these things. Now, for comparative purposes, the international standard atmospheric lapse rate based on the meteorological data has been adopted and defined. Specifically on the average in the middle latitude, the temperature decreases linearly with elevation up to 10,000 meters. So the temperature decreases linearly up to about 10,000 meters. So which is 10.8 kilometer. Average temperature at sea level is 288 and decreases to 216. So the standard lapse rate that is there, which is 216.7 minus 288, 10 meter, so it is 0.0066 degrees C by meter. So that's the standard lapse rate based on international condition is roughly 0.66 degree per 100 meter. That is as per the international standard. Okay. We can see typically also the temperature profile changes from day to night due to heating of the Earth's surface. So we can kind of have a representative graph. So this is T, this is height. So typically this is let's say Z1 or Zi. So Zi here is called the inversion height. Okay. So here before sunrise, this solid line shows the some kind of a temperature profile, and this decreases with increasing height near the ground and reverse after sunrise, which is the this kind of a dotted or dashed line that changes with the sunrise. So air is usually heated near the ground and the temperature gradient close to Earth's surface increases with height up to a height, some Zi. So the surface layer of air up to this height is called the um, so this is known as convective or mixing layer. So up to this height it is known as. Above this particular height the temperature profile reverses. This is how the lapse rate is taken into consideration finding out the stability. In general, dt by dz, if it is greater than dt by dz Adiabatic, this situation is a stable situation. Okay. Obviously, one has to note that the international lab state seldom occurs in nature. So this is why you need to have those meteorological data to monitor these things around your airports worldwide to determine the actual lapse rate. So you have this daily balloon surrounding those airports. Also, to have stability, to have stability, it is not necessary for an inversion to exist. When one does exist, the atmosphere is even more stable. Okay. So this is how the atmospheric boundary layer stability can have some impact, and obviously this can lead to different stable to unstable situation, and or maybe staying at neutral stable condition. So what it does, that gives you an idea and all these things. Obviously, when you talk about this atmospheric boundary layer, the one of the important issue is the turbulence, which we have seen some basics of the turbulence, but now we are go a little bit more details about those things, how this impacts the boundary layer, and in turn the calculation of the wind energy and so on. So the turbulence here in the wind is usually caused by the dissipation of wind's kinetic energy into thermal energy via the creation and destruction of some smaller eddies or gusts. Obviously, any turbulent flow, they can, I mean, it is more or less like an, if you look at the speed, so this could be very much fluctuating and random in nature. So every flow will have some kind of an mean. Okay. Obviously, the feature to characterize is that one has to talk about turbulence intensity, wind speed, probability density function, autocorrelation, integral time scale, integral time scale or length scale, PSD or spectral density. So we have very briefly talked about these things and how they are interconnected to those things. So, so when you talk about the turbulence, so this field is essentially 3D in nature. So the impact can be sensed both, I mean, in all longitudinal, lateral, and vertical components. Obviously, longitudinal component in prevailing wind direction. So if I say that longitudinal in prevailing wind direction is defined at UJT, the lateral component which is perpendicular to U is at T, and the vertical component would be WZ. So essentially these are, if I have a vector, these are all these components U, V, W. So that's the, so once you have, as you have seen this particular the instantaneous velocity, let's say u, which could be having two components. One is the mean component and the fluctuating components. So this is mean, and then let's say, so here this is the fluctuating component. So that means the flow will have some mean around that and fluctuating component. So if you have short-term mean of the wind speed, then you can, for a, let's say, time period of delta t, then you can find out this mean. So here u is the mean. We can write 1 by delta t, 0 to delta t, u dt. Okay. Also, you can collect a lot of samples, and using the mm, collected sample, let's say sampling interval, is, let's say, delta t is del t, and you have collected number of sample. Then your delta t is ns delta t. So you can write u is 1 by ns summation of I to ns ui. So this also we have seen that how. So this is, one can think about short term average longitudinal wind speed. So this is often used in time series observation, and also we'll use this in our discussion. So next thing that you need to look at is the turbulence intensity. So that's a basic measure of turbulence in the turbulent flow field. Okay. So it's kind of a define the ratio of the standard deviation of the wind speed to the mean wind speed. So if my turbulent intensity is like that, then we can write sigma u by v. So this also you have seen. This calculation, both the mean and standard deviations, usually calculated over a time period longer than of the turbulent fluctuation, but shorter than the periods associated with one type of the wind speed variation. This sigma u is essentially 1 by ns minus 1 summation of 1 to ns ui minus u. That's the typical turbulent intensity, varies from range of 0.1 to 0.45, and depends. The, I mean, in general, the highest turbulent intensities one can observe at the lowest wind speed, but the lower limiting value given depends on the location, specific terrain features, surface conditions, etc. So, and now the other thing is the wind speed probability density function. This also we have seen that, because wind speed has a variation over a time, and those variations, to capture those variations, so we have looked at least the Gaussian distribution, which is normal distribution, Weibull distribution, and the Rayleigh distribution. So we have seen the probability density function of those distributions, because these distributions are very important to have in. And also we have looked at the property of autocorrelation. So how they are correlated the data and the between two spatial locations and how closely, and we talked about that as well. Now, what, and then we have found from autocorrelations, we can find out the integral length scale, time scale, all these. So that's how from the autocorrelation function you can find those out. And then power spectral density, that is another thing that we have seen, that is PSD, or spectral density function. So this is used for kind of an dynamic analysis of the system. So often this number of power spectral density function are used as model in wind energy engineering. And when the representative turbulence or spectral densities are unavailable. So there are theoretical models which are available for different flow fields and things like that. So those are kind of used. So now another thing is that wind speed variation. Wind speed variation with height. So wind speed also varies with height. Then you will have, I mean, we have seen that the variation profile could be like that. So there is a variation of the speed with height. Hmm. So this is essentially going to lead to wind shear. And wind shear influences both assessment of wind resources and the design of the wind turbine. Because assessment of wind resources over a wide geographical area might require that anemometer data for a large number of sources. Again, from design aspect, a rotor belt failure life will be influenced by the cycle loads, resulting typically from rotation through a wind field that is varying with the. So this variation with height, or indirectly which we term at wind shear, this has impact in design. This has impact in assessment. So this is an important parameter. Typically, there are two mathematical models which exist, or laws, one can say. Generally, what it has been used that this vertical profile of wind speed over a region of homogeneous flat terrain, that is field deserts. And the first approach is kind of having a log law, okay, and then second is the power law profile. So kind of if you see this two-dimensional feature, this is the mean variation of the profile. Actually, this can vary like this over this thing. Log law, or logarithmic profile, which is often known as log law. So, I mean, there are different ways also to arrive at the prediction of logarithmic mean profile. So, what we can say that near surface of the Earth, the momentum equation reduced to del P by del X equals to del tau xz. So here the direction wise we can say that X and Z, these are the direction. So P is the pressure, tau xz is the shear stress in the direction X whose normal coincide with Z. Pressure is independent of Z and integration yields that tau xz, tau 0 plus Z del P by del X, where tau naught is surface value of shear stress. Since near the surface the pressure gradient is small, so what we can do, we can neglect this term. So we can neglect this term because near surface, assuming that pressure gradient near surface is small. So with that, and also we use Prandtl mixing length theory, so which gives us tau xz is rho L square del U by del Z square. So rho is the density of the air, U is horizontal component of the velocity. So now if we combine this and this, what we get, del U by del Z equals to 1 by L tau naught by, which is U star by L, where U star is tau naught by rho. So this is my friction velocity. So if we assume a, let's say you assume smooth surface, then L equals to kappa Z, where kappa equals to 0.4, which is known as von Karman constant. So then we can integrate this from Z0 to Z, where Z0 is surface roughness length. We get U of Z star by kappa ln Z by Z. So this is known as logarithmic wind profile. So this is what you get, which is also known as the log law. So obviously this further we can develop and come to a final expression for that. So this logarithmic profile is one of the profile which has been used to calculate the wind shear and things like that. Okay, so we'll stop here and we'll continue this discussion and finish it up in the follow-up session.